Good afternoon, everyone. Today I want to discuss with you the central limit theorem, which is a really important and in many ways very exciting idea in statistics. So I'm going to skip over some material that's specific to my class this semester that I'm recording this at the UW and get straight to the motivation. Here to the right we have Francis Galton. Galton was a very important and influential figure early in statistics, but also psychology and genetics. He is kind of an unsavory figure who had some opinions about heredity that today we no longer think are true, and are opinions that are generally speaking not very politically correct or pleasant things to say. But in many ways, he also is responsible for much of the statistics that we continue to use today. And I think it's kind of interesting to revisit the works of these old fogies, so to speak. We've actually already seen in our discussion of regression original data straight from Galton himself. And I thought it might be kind of interesting to hear what he had to say about the central limit theorem, because it gives you a sense of how exciting this idea can be, even if you don't agree with Galton on other things. So this is what he had to say. I know of scarcely anything so apt to impress the imagination as the wonderful form of cosmic order expressed by the law of frequency of error. The law would have been personified by the Greeks and deified if they had known of it. It reigns with serenity, amidst the wildest confusion. The huger the mob, and the greater the apparent anarchy, the more perfect its sway. It is the supreme law of unreason. So, pretty, almost emotionally charged language from Galton here. And I've actually mentioned this fact about the Greeks before, which is funny, because the Greeks actually did have cults to different mathematical ideas. If you're interested in this, the Pythagoras cult is something to read up on. But people had some very strong opinions that sometimes, I can't remember if this is apocryphal or not, but allegedly rose to the level of basically these math gangs murdering members of rival math gangs. I can't remember if that's sort of like a tall tale or not. But anyways, you get a sense for how powerful these ideas are. That's really what I'm kind of interested in showing here, that these are very exciting, and indeed, in many ways, the development of modern statistics, and along with it, things like ChatGPT. I'm going to say ChatGPT a lot this lecture series because it's just come out during the summer that I'm recording these, or spring rather. But yeah, any of that fancy AI stuff, all of that machine learning stuff, in principle, is basically just statistics. And so you can see Galton wasn't wrong about this particular claim he made, that these ideas have enormous power. So here's the plan for the lecture, though. I do want to review the binomial distribution. And the reason I want to do that is that the binomial distribution is an example of the central limit theorem, and it's one that we've been able to derive by hand. And later versions of the central limit theorem in a class at this level, we aren't actually going to derive more than a couple of key properties, but we won't actually be able to derive the form for the distribution, in part because the form of the normal probability density function is pretty scary looking. At a certain point, if you continue on in statistics, you'll just kind of involuntarily memorize it. But if you don't continue on, it looks like terrifying, and you should avoid learning it before you really need to, basically. The binomial distribution, by contrast, although it does really work your Algebra 2 muscles, is something we can derive with Algebra 2. We don't need to derive the true kind of general form of the central limit theorem. We would need multivariable calculus. Okay, so we're going to start with the binomial distribution, and then we'll kind of generalize. But really, if you understand fundamentally what's happening with the binomial distribution, you understand sampling distributions. So what does the binomial distribution do? It gives us a model for how probable any possible number of successes k on some dummy variable d is given a sample of size n. So there's a variety of different things happening here. There's a variety of unknown quantities. So we need a value for p, which is the population mean of d, the dummy variable. It's either known, as we saw before, where we, for instance, we're examining methods of breeding plants, or we were assuming that we just knew, generally speaking, how many people would choose to attend college once given a letter of offer. These are things that we or more common examples too would be the probability of flipping a heads when you flip a coin, or rolling a multiple of 3 when you roll a fair die, which incidentally is 1 in 3 since 3 and 6. So those are situations that are somewhat rare and oftentimes involve like physical phenomena in a way that's going to be uncommon in social statistics. And we need to kind of supply for the binomial distribution, I'll show you in a second, one of these two things. So basically the value of p or the value of k. But in principle, we could know either. So what's the point? Well, the binomial probability mass function looks more and more normal-ish as the sample size grows. And again, n is the sample size. It's not the number of replications. In practice, we don't need to do any replications. If we have a larger sample size, we don't consider that. Like if we have a sample and then we suddenly get, oh, this, that came late in the mail, we got a whole bunch more responses. That's not two samples. I mean, it is, but you should not consider it two samples. You should consider it one large sample because you don't have to build a sampling distribution or a binomial distribution by hand. The key point here, and it might sound like I'm getting off into the weeds, but this is actually the whole idea, is that we know what the distribution of the number of successes looks like across all possible samples without having to take all possible samples. So one way to think about it is, in a very simple way, it's just a time-saving device. We can't actually take all possible samples. We'd be stuck here all day. We'd be answering some dumb question about, the mean level of education or the population probability of having completed college. We'd spend our whole lives doing that, right? And in fact, it would be easier to just take a census of the population, although that would not also be easy. So the point is we can actually safely say what the distribution of the number of successes looks like in a sample of fixed size n if we know p, and we only then need to do one replication in practice. Or if we don't know p, as we saw in the last lecture, we can just take a sample and acquire k, and then say how probable is this k given some little p. So this is what our formula looks like here. And we read this as the probability of a random sample having the number of successes k is equal to n choose k times the probability of a success on a single trial to the k times 1 minus that probability, or the probability of a failure, to the n minus k. Let's think about a concrete example of that. So let's say we are interested in the probability that 5 out of 10 people in a sample will be married. And let's say that the GSS data that we have for 2018, which tells us that there's about a 43% chance of being married, are a good guide to the population, right? And so then what we would do is we would say, okay, the probability of 5 people right in a row being married is 0.43 to the 5. And that represents the probability of the first 5 people you draw being married, or the last 5, or every other person, or whatever, but it only represents that set of people, right? It only represents the probability of those 5 people. So we need to do 2 other things. One, we also need to account for the probability of someone not being married, right? So we would then say, okay, multiply we said 0.43 before, so 0.57 to the 5. Or we could say, maybe, let's do even a slightly clearer example. Let's say probability of people being married in the 10-person sample equal number of people is 4, just so the numbers aren't the same. So we would do, 0.43 to the 4 and then 0.57 to the 6. And what that represents basically is the probability of some particular sequence of 4 successes and 6 failures. And that's going to be the same whether the 4 successes all happen first or whether you have them interspersed, right? The problem is that that's going to give us absurdly low numbers because we don't actually want just the probability of any particular sequence. We want the probability of just some combination, basically. So how many ways could we choose out of the 10 people before they're selected, so treating them as random variables, each person a random variable, how many ways could we choose 4 of them to be successes? That's given by 10 choose 4, which would be this quantity here, right? And we can go ahead and plug this all into the online stat book, the binomial calculator, so we'll do that now. And I'll show you kind of what that would look like. We could also do this by hand, but this is just meant as a review. So we have 10, probability of 0.43, And then we would say the probability, it happens to be centered on 4 already, it would be this here. So the probability would be 0.2462. And that's what results. We can actually show using Wolfram alpha how that comes from the formula. So we say here 10 choose 4 times 0.43 to the 4 times 0.57 to the 6. And that's equal to 0.246 and change. So you can see that here. I didn't rig this. I literally just looked up right before I started lecturing. You can see here I did not know the population probability of marital status, so I looked it up. And then I'm just able to do that like that. So it's a very powerful formula. What we could also do, notably, is if we didn't know the population probability or we were uncertain about it, right? So like let's say before drawing that sample from the GSS, we thought that the population probability was 0.5. Then what we could do is actually, let's show this now. What we could actually do is come here and say, okay, probability is 0.5. Now what's the probability of 4 people being married? And you can see it's 0.20. And you might say, well, it's hard to weight that evidence really. And I would agree with you. There's a variety of different ways to think about this. One way that we do it in what's known as frequentist statistics is we then say, well, we don't care about just 4, we care about 4 below. So we'd say below 5 here, so 4 and fewer. And we would say, okay, there's a 0.377, or in other words, about 38% chance of that. And we would say, okay, that's not wildly improbable. That doesn't change my mind about the postulated probability of 0.5. There's other ways of doing this in the so-called Bayesian tradition or in the likelihood tradition, but we're not going to deal with those here. So in this frequentist tradition, which I personally don't find the most convincing, but it's the easiest way to teach at this level, and it's a respectable brand of statistics, I'm more drawn in by the likelihood paradigm, we would go with this particular setup here. Okay, so that's one way to think about evidence here. And you can, again, do the same calculations here. So now we would say this is 0.5, this is going to be 0.5, and we have the same thing here. We don't need to change the 10 choose 4. And you can see we would get 0.20. Now, to calculate this sum here, we would need to iterate the same thing or to put it into the math input here. And we could do that pretty simply like this, but I'm not going to walk through that. The point is we can usually turn this over to computers, but it's important to understand what's going on underneath the surface, basically. Okay, so that's the binomial distribution. That's the whole logic there. Some facts about it. The mean of the distribution is n times p, and the variance is n times p times 1 minus p. The intuition for that is pretty straightforward, right? If you have a population probability p, and then you have n people, then in theory, it should just be that population probability times n. So in our previous example, the distribution for, when the population probability was held to be 0.435, that would just be 4.35. You can't have 4.35 people, but that would be the mean of this distribution. And then the variance is pretty straightforward. The variance for a dummy variable is p times 1 minus p. And it turns out, and I'll actually go into some of the details of this proof later on, that when you add up all the variances of a set of n random variables, when you get a random variable that is basically n other random variables summed and they're not correlated with one another, then you can just add the variances. We'll come back to that proof. Just as a friendly reminder, we've got a lot of stuff going on here. So you want to think about this as kind of a complex function. Capital bold P is the binomial probability. It's the output of this probability mass function. N is a fixed constant that has to be established for this distribution to be defined. And then K and little p can both vary, right? So we could, and generally speaking, however, we let K vary, but K might actually be something that we know, and we just look at the distribution as if we don't know K. And then P, in theory, should be, quote unquote, something that we know, but a lot of times in practice we just sub in something and then we kind of, again, treat K as variable. That's how we produce those graphs. But in practice, we'll often actually know K and not know P, so then we pull up that probability mass function as if we knew P, and then use that to let us, let that guide our decisions about whether or not that's a plausible value of P. So we've gone over what the formula means already. And then I've already said all this stuff out loud. I prefer not to read off of slides. So these slides are here for reference, but we've just kind of said all of these things out loud. And this is another example with left-handedness. We're not going to go through that. So what's the key idea of this lecture? The big idea is that this logic generalizes to means, not just counts, and that generalizes to means of both dummies, so sample proportions, and quantitative variables, so regular old sample means, y bar. That's pretty exciting. So let's dive in. And we've gone over this material about the binomial distribution. So this is what the binomial distribution looks like for, say, a fair coin, right? And when we have a sample of size 1, even if we simulate doing trials and experiments of size 1 a million times, note that the distribution of that single coin flip just looks like this probability mass function that we could have derived from the outset by just saying, well, I know a heads has probability 0.5 and a tails has probability 0.5, and the only two possible values of the variable are 0 and 1. I could have drawn that probability mass function straight away, right? I didn't need to do any experiments to do that. So notably, the information that we get when we have a larger sample, so when we have a sample of size 5 or 100 or 500, the information that we get is that it comes from a distribution that looks like this, or looks like this, or looks like this. These can be derived with the binomial distribution. I also just showed what it looks like when you simulate it here, and the simulation notably produces a really nice regular looking graph, okay? So the idea is that the binomial distribution gives us this really useful information about how samples are, basically what would happen if you took very many samples. And that's the logic that then lets us say, okay, what does the sampling distribution look like, conditional on certain facts, and then is my sample consistent with that fact or not? So I wanted to review the concept of random variables for a second because I've already mentioned them a couple of times in ways that could potentially be confusing. And once you get a handle on this, the central limit theorem is really straightforward. So why do we care about this difference between the upper left figure and all the others? Again, the figure at the top left is for individual outcomes. Yes, there's very many simulations, but notice that this looks just like it would look if you just wrote down an abstract guess at what it would look like when you did this in the long run. So it's very intuitive, right? We know certain physical facts about what happens when you flip an individual coin, and we don't really need to worry about too much else beyond that. This here was kind of irrelevant. And individual outcomes are what we care about. So even if we care about a group level property such as the spread of income or the mean income, these are still functions of individual level properties. And so that's really the kind of thing we're concerned about, right? But notably, we don't observe just one person. And there's a good reason for that. A sample of n equal to 1 is not very helpful. So although we want to do inference on the population distribution of individuals, we generally observe groups or samples. And we can use those observations to make guesses about population parameters, like a mean or a regression slope. But counterintuitively, group level properties that we get from the sample, such as the mean, have probability distributions of their own. These are called sampling distributions. They describe the spread and center of all possible sample means if we took infinite samples. And this is not infinite here, but it's very many times. So these are a million replications of a sample of size 5, 100, and 500 here. So that's what that's showing. So these sampling distributions generally don't resemble the individual population distribution, and that's a good thing. The sampling distributions often come from or resemble known distributions such as the normal probability density function, which is really exciting because it lets us do inference on those things in a way that would otherwise be challenging. But it is important to clarify now what a random variable really is. So before any sample is drawn, any hypothetical person's income or education or whatever you like is an RV, a random variable. So a sample of n equal to 1,000 observations, and let's assume you don't have any non-response, just to keep it simple, is actually a realization of 1,000 random variables. So each person's income or education before we selected them was a random variable. That's kind of counterintuitive because we just see the realization. So for being exact, we don't actually observe a random variable. And when we talk about variables in stata, for instance, we don't really mean a variable. We can't actually observe a variable. We observe a vector of realizations on that random variable of dimension n. and that's kind of counterintuitive, right? Because we often still say, well, oh, the variable education in Stata, the variable income in Stata, but these are not actually the random variables themselves. And moreover, each individual person themselves was a random variable before we drew them, right? So it was a random variable of size 1, which is a really interesting fact, and it's something that kind of leads us to this key idea. What that means is that the sample total, in the case of the binomial distribution, or the sample mean, as we'll discuss today, is itself a random variable, but it's one that's different to these individual random variables. So a sample mean, or a total, is a composite random variable. It has a strongly deterministic component to its underlying distribution. The shape is clearer, there's less noise, and it, generally speaking, does not have to look like the distribution for an individual. That's the whole magic of the central limit theorem. So let's look at an example of that. I want to actually just show the outcome first before I give the formal statement. So this is what that looks like. Here we can see a situation where I took a fictional city, and it's a fictional city that's based on the CPS, but the details don't matter. And I'm saying this is the whole population. So I know I'm going to use data where I have the entirety of the population. And it's population where income, much like it is in the real world US, is skewed. And we're just going to call this city Springfield because I'm a big Simpsons fan. So this is what income is distributed as in the city of Springfield. And a city can be a population, right? So we care about income in this city. What would happen if I took 5,000 samples of, say, n equal to 10,000? So this is a city of 200,000 people or something. What if I randomly subsampled Springfield and took 10,000 people, right? So basically 1/20th or 5% of the population. Then if I plot all of the means of income and I do that 5,000 times, this is what the distribution looks like. And if I did it 1,000,000 times, which is computationally too taxing, but not too taxing, it would just take forever. But what would happen? This would get increasingly normal. And the reason for that is nothing to do with computers or computer simulations. It's because of this basic idea that when we, and it's kind of like the binomial theorem, right? Or the binomial distribution. That's probably the best way to think about it. The idea is that, pardon me, sorry. The idea is that when we take a sample and we add together everyone's income and we take the mean, that sort of neuters the influence of these high income outliers here. So when these people are included in the sample, yes, that's probably pulling those individual samples up here. But we don't always observe those people, and we also do observe some lower bound outliers here too. And really fascinatingly, this sample is actually centered right around here, around this mean here, right? So you can see that the mean of the sample is 25.8 or 9 or something, which is happens to be the population mean here. But notably, there's this really tiny spread, right? So not only is there kind of this strongly deterministic component and centered at a meaningful place, the true population mean, but the deviations from that are basically governed by this kind of law of inverse proportionality. So the farther away you are from the mean, the true population mean, the less probable you were to observe a number of samples in that region. So when you get over here, you had just a handful of samples there, and then kind of as you get closer and closer to the true mean, the probability of a sample in that range or that range got higher and higher. And the idea is that when you basically have a sample that is trying to estimate some known fixed quantity and deviations from that are random, so it's not like these people don't exist, and it's not like they are in some sense random, but whether or not they end up in the sample and how many of them end up in the sample is random. And the idea then is that you're not going to consistently get these people, and these people will be present in the sample in basically accordance with how weird they are in the population, and how weird they are in the population is going to influence the mean. So these people are really weird in this distribution. There's not a ton of outliers here. That means that they exercise some influence on the mean, but not as much as they would otherwise. They're true outliers. And that means that basically this idea of the inverse proportionality of error applies. So let's state the central limit theorem formally. So what does it tell us? It tells us that above a fairly small n, sample means, much like the counts of successes, also have a roughly normal sampling distribution. Here's an example of a formal statement. This is from Wooldridge, his Econometrics Without Matrix Algebra textbook, which is a nice intermediate textbook. If we let, and by the way, this is why I'm telling you this about random variables here. You'll see this all the time at higher levels, and it can be very confusing. Let y1, y2, up to yn be a random sample with mean mu and variance sigma. Then z sub n, so in other words, a standardized version of the mean, so this mean here minus the true population mean over this quantity here, has an asymptotic standard normal distribution. So let's break down all of those parts, because this actually tells us everything that we need to know about the central limit theorem. So first of all, we've got all these y's here. These are all random variables. So again, before we draw the sample, we don't know who person 1 or person 2 is going to be. That's a random variable. We could pick you or pick me or pick someone else. So that should be treated as a random variable that will have a draw of size 1, and then the sample mean should be understood as the sum and then division of n random variables. And that'll become a little bit important later on. So we know that this has a mean mu. So this is the kind of random sample. Pardon me. This is the random sample here, but the population mean is mu, and the population variance is sigma squared, pardon me. And we'll just should probably make that a little bit clearer here. So then the idea is that the sampling distribution for this sample mean has a mean of mu and a standard deviation of sigma over root n. And what that means then is that when you subtract off the mean mu and divide out by the standard deviation sigma over root n, that means that this is just a z-score, basically, right? So this is normally distributed as a random variable. And that's what this says here. So let's go ahead and we kind of went over what all this means here. So remember, this is what the central limit theorem looks like in practice. We can go ahead and actually look at this also in practice as well using this applet here. So let's do this together. You'll come here. I'll give the instructions here. So this is our population distribution. And why don't we go ahead and change this to a skewed distribution, right? And then what we're going to do is draw a sample. And what we'll do is let's just animate it first. So we'll draw a set of 5 here, right? And so this is a sample of size 5. This confusingly refers to reps, which I don't like. This is actually the sample size. So it's a sample size of 5. We can take another sample of size 5 and note that that plots a second mean down here. So this is just a given sample, and then this here is what they're kind of piling up as. Let's change n to make it a little more realistic. Let's change it to 25. So this will take a little bit longer. Notice that the sample is skewed, right? So the sample looks like the parent population. We'll do one more. And this happened to give us the same mean. Let's maybe do one more just to show that we'll get a different mean. But the point is you can see that the sample looks pretty skewed. So it looks like the known population. And even if we don't know the population, we might get a sample that's evidently skewed and say, oh, yeah, this looks a little skewed. Uh-oh, I wonder if I can trust my inference. But note that the distribution of sample means across all possible samples is going to start looking more and more normal. So let's speed it up a little bit. Let's do 5. Add another 5, 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 add another 5. We can animate one more to just see, again, that this is basically just putting together those means. So this will drop a blue square somewhere here when it's done. Okay, so it dropped there. But then we can continue adding another 5, another 5, another 5. Let's go to 10,000. Another 10,000, another 10,000, another 10,000. Let's add a couple 100,000s. And you can see that once we start adding more and more means here, so here I'm simulating taking 100,000 more samples of size 25, taking the means, and then adding to the histogram of means here. So you can see we've got a lot of repetitions or replications here, right? So this is over 1 million. It's 2 million and change. So this is showing us that the distribution basically at some point becomes normal looking and then doesn't change, right? So if we just add yet one more sample here, you You can see it, technically speaking, plonked somewhere down on here, but it didn't make any visual difference. So we didn't see a really wacky mean out here or anything like that. So that's a visualization. Now, again, I want to hammer this point home. This is a very useful tool for learning, right? It's a very useful tool for learning the central limit theorem, but in practice, we only have one sample. So in practice, what do we have? We have this. We have this sample here, say size 25, and we only have this one mean here. But we know theoretically that it comes from the following distribution. It comes from this distribution here. That's the magic of the central limit theorem. And this is what this should look like if you want to play around with it at home. So here are some key facts about the sampling distribution. The sampling distribution of a mean is centered at the true population parameter mu. So we saw that before here. So x bar, the sample mean, is an unbiased estimator of mu. In other words, that means x bar is a good guess about the value of mean in the population. There's not any reason that it's going to be, upwardly or downwardly biased, which is not always the case. We've seen some situations before where we have estimators that, for instance, if we take the sample standard deviation and we don't divide by n-1, but we instead divide by n, it's going to be a biased estimator, right? So that's why we correct for that. Pardon me, sorry, I'm still getting over this this cold here. So that's an important fact about the sampling distribution. The standard deviation of the sampling distribution is given by sigma over the square root of n for a sample of size n, and we'll prove that in a second. You might wonder, though, right away, how we could possibly know sigma and not mu. So we've been saying that we're going to use this to do inference on the population mean mu, and we're, however, assuming that we somehow know sigma. That's a really good point, but it's one that has a simple solution that we'll see later on. So for now, just don't worry too much about that, and we'll kind of come back to that point. So here you can see mu on the left here. This is the true population distribution is 25.82. You can see that that appears to be the mean here. And sigma is 17.23. On the right, we have the mean 25.83, and the standard deviation is not exactly there, but it's close, right? So this is a sample of size 10,000, right? So hopefully you can quickly do the algebra, or just really the arithmetic in your head. So that means that the square root of that is 100. So we divide 17.23 by 100 and we get 0.1723. So 0.163 is pretty close. So we're almost done with just the basic idea of the central limit theorem. I want to give two motivations, though. The first is this motivation for hypothesis test. So we've been talking so far about descriptive statistics. How do we know if our conclusions generalize to the population? Well, we can use facts about the sampling distribution to do that. So if we know what a bunch of samples from a population with a certain mean or proportion would look like, we can figure out how weird our results are given that. If the results are very weird, that's evidence against the null hypothesis. And we saw the last time, we saw this discussion of basically the situation with the plants, right? Where I made up this example that wasn't in the book, but was hypothetical. What if we had this set of plants and we knew, like we can just pull up the discussion here. We were curious about whether or not the population probability really was 0.75 that a plant would be red. And then we get a sample of size 60, and we observe the number of plants with red blossoms is equal to 40. So then we can come up with this population distribution that looks like this and say, okay, what's the exact probability of seeing 40 or fewer plants with red blossoms? And that ended up being a relatively small number, and so that gives us a reason to cast doubt on the hypothesis. That's one way to do it. Here's another closely related technique. We can also say that a certain proportion of samples falls within plus or minus a certain number of standard deviations of the mean when we know this fact about the sampling distribution. So for instance, a given sample that we take comes from a sampling process that gives a sample mean that is within, say, plus or minus 1.96 standard deviations of the true mean 95% of the time. And this 1.96 comes from those facts about the normal distribution, and this bit here is due to the fact that this is the standard deviation of a sampling distribution. So, and this is a technique we'll use very often in the remainder of the class. It's called constructing a confidence interval. If we add and subtract 0.196 times the standard deviation of the sampling distribution, known as the standard error, by the way, to our sample mean x bar, this range will include the true population mean mu 95% of the time. Here's an illustration of that idea from our book. So the book gives us a situation here where we've got 25 samples and we add and subtract to that sample mean 1.96 times the standard error every time. And notice that in one situation we do miss the true mean mu here, but in all the other situations we manage to capture it. And so that's the idea of constructing a confidence interval. We'll pick up with that in some detail the next time we discuss this, but I just wanted to give a sense for right now, why is this useful? What's cool about it? Finally, I did want to distinguish, this is the last slide of the lecture, the difference between the law of large numbers and the central limit theorem. That was redundant, just distinguish them. These two things are often confused, and they're actually very separate ideas, and we aren't really going to use the law of large numbers. In fact, I wish the book really just didn't talk about it, but I do want to eschew any confusion here. Wade off any confusion, not eschew. So what does the law of large numbers tell us? It tells us that as our sample size gets larger, the mean of the sample gets closer to the population mean. That's pretty intuitive. We saw it with our coin flip simulation. If we take a bunch of samples, this approximates the true sampling distribution. So we used the law of large numbers before to, say, prove that the central limit theorem was true. Or not prove, but pile up evidence for it. So I took a bunch of replications. But the central limit theorem tells us that a random sample from a population with almost any old distribution has a count or a mean or a proportion drawn from a roughly normal sampling distribution. And this means that the central limit theorem is really what matters. We don't need to take more than one sample to know a ton about the plausible values for the population parameter. So the law of large numbers is actually kind of overrated because it only tells us about the behavior of a sample as n gets larger, which leads to, for instance, a branch of theory known as asymptotic theory. But it's not really that necessary at this level, and it's really kind of cool that we just know this fact about the central limit theorem without taking multiple samples. So I think that's a reason that the law of large numbers is a little bit overrated in the CLT, remains this very fascinating fact. So that's where I'll cap the lecture. Next time we'll talk about the construction of confidence intervals.